All right, so today we're going to talk about our next type of chemical reaction, decomposition reactions. These ones are actually pretty cool because there's a whole lot of variety of them in terms of what they can do, what they can form, and how they're used. But essentially, the big idea behind these types of reactions is that they're going to be the opposite of synthesis reactions. So if we think back to everything that happened in synthesis, where we had multiple reactants forming a single product, that is the opposite of what's going to happen here. In a decomposition reaction, we have a single reactant that's going to be breaking down into a bunch of smaller products. Now, the same way a synthesis reaction was almost always exothermic because of all those bonds being formed as we make this larger compound. Here, we tend to have a lot of bonds being broken apart. So generally, these reactions end up being endothermic overall as we break a lot more than what we form as a result. Now, because of this, that initial part of the curve is usually really, really high. There's a large activation energy needed for these reactions, generally speaking. So those that do tend to occur naturally usually happen at a fairly slow rate and usually need to be initiated by a catalyst or a large input of energy. And then once that energy is no longer being fed to the reaction, it slows down incredibly or stops completely. Now, for the predicting the products of this, there's not a hard and fast rule for just overall decomposition reactions. In synthesis reactions, we had said that they come together to form a single product. So it was basically just what is the ionic compound or covalent compound that they would form together. For combustion reactions, we had our rule for hydrocarbons of always carbon dioxide and water. But for decomposition reactions, it depends on what exactly is being decomposed. And generally, these are ionic compounds that we're talking about with decomposition, but it is possible with covalence as well. So it depends on what the ionic compound is that's being decomposed. And the best way to predict these, we're going to go through a couple of common ones, is to look at what is the anion, because generally it's a polyatomic anion that's being broken apart and releasing different gases and stuff as we get into more stable compounds. For a lot of these ones, we decompose them and we give that activation energy through heat. So sometimes this is called thermal decomposition. But for example, when we have a carbonate compound, it's going to always decompose into carbon dioxide. And then what's left over is just the metal and the oxide. So in the example there we have this calcium carbonate. When that's heated up, it will evolve or emit carbon dioxide gas and leave behind just the calcium oxide. Sodium bicarbonate does something similarly. However, it has that extra hydrogen in there that the previous example did not have. So that hydrogen actually joins up with some of the oxygen atoms that are being released to form water along with the carbon dioxide. It's actually that second reaction, which is what causes cakes and pancakes and cookies to rise. Sodium bicarbonate is also known as baking soda. So that's that decomposition of the sodium bicarbonate that releases the gas inside of the baked good that causes it to rise as that gas gets trapped by the rest of the dough. Some of it's also because of the reaction it does with the acid in the dough, which also produces gas, but we'll talk more about that when we get to acids and bases. Other thermal decomposition reactions would be chlorates. Chlorate, for example, in this one we use potassium chlorate. When it's heated up, it decomposes into the metal chloride, right? Because it no longer has carbon for the carbon dioxide here. But it turns into the chloride and it releases oxygen gas. Now, these types of reactions are often used when oxygen gas is desired for a product. The reaction itself isn't overly exciting. However, when we feed oxygen to other things, that's how we get combustion reactions. So often these types of compounds are called oxidizers because they produce the oxygen, which is used as an oxidizer in combustion reactions. So this allows combustion reactions to not only happen faster and more vigorously and more energetic really, really fast, but it also allows these types of reactions to occur where not as much oxygen from the atmosphere would be available. So meaning like inside of closed containers or in space, that kind of thing. So for example, these types of compounds are often included in things like rocket fuel, gunpowders, explosives, to provide that extra oxygen to the hydrocarbons for the combustion reaction to allow it to happen at a much greater rate. It's also what's used for the famous dancing gummy bear experiment, which we're going to look at in a moment, because it provides so much oxygen to that environment that allows it to combust rapidly compared to what would happen under normal like atmosphere conditions. So the dancing gummy bear experiment. First, we're going to have the thermal decomposition of potassium chlorate to produce oxygen gas, and then we're going to be doing that by heating up the potassium chlorate, getting it really, really hot. So inside that test tube is going to be really, really hot, a really hot environment. You'll see some liquid melted potassium chloride at the bottom, and there's going to be a lot of oxygen gas in there. And when we drop in a gummy bear, which is chock full of sucrose, it's going to react with that oxygen gas in that hot environment to undergo a combustion reaction. All right, let's take a look.
So here you can see Mr. Grodsky heating up the potassium chlorate with the torch. And it's starting to melt into the liquid there, decomposing and release the oxygen. So now you have a really hot system with all of the oxygen gas and the molten potassium chloride. And the gummy bears he just held up are going to be added into it. And then the oxygen there will react with the sucrose, the sugar, and the gummy bears for the combustion reaction.
So without further frost, let's make these gummy bears dance! Obviously a very exothermic demonstration. If you're wondering where we're pumping out that gas, everyone knows, right? Elementary playground. No.
So you can see in the beginning the reaction was a lot more sporadic, jumping up and down as the gummy bear was being bounced around as the combustion was happening. But as the reaction continues and the sucrose in the gummy bear starts to melt, it doesn't bounce around as much when we get this much more constant reaction that you see happening here now.
Really, just a transfer of electrons. KCl3 is whipping the electrons away from the sugar.
Still one of my favorite reactions, and if you notice the purple color kind of as it was going on, if you remember back to the flame test lab, when we had that one swab that produced that purplish pink flame, that was potassium chloride. So here that same color is a result of that heated up potassium chloride in the bottom of the test tube from the decomposition reaction once it starts combusting the sugar. Another fun, exciting decomposition reaction occurs when we have hydroxides and oxyacids. Now, hydroxides, when they decompose, they just form water and the oxide. Generally, hydroxide compounds are pretty caustic. They're what make really strong bases, so this is one way to kind of neutralize them to make them a little bit safer to handle. Oxyacids, though, when they decompose, they form water and carbon dioxide. Now, this example that I chose here with H2CO3 is carbonic acid. That's what they put in sodas so that when they start getting heated up by the atmospheric temperature and you open up the bottle, it releases lots of carbon dioxide. That's what makes up little bubbles in your soda. Now, generally, this happens fairly slow, right? It is a decomposition reaction. It's endothermic. However, if we drop something in to catalyze the reaction, like a little bit of Mentos, with those little pores on there that give it a place to trap the CO2, we can cause a decomposition reaction to happen really, really, really fast. And this is what causes that famous Mentos in Diet Coke fountain experiment. Right, let's take a look.
3, 2, 1, pull. Good. Ah! Is that? Tell me that that's not awesome.
Is
that?
That's
okay,
awesome.
No, that's so sorry.
That's okay.
Look at you. You are.
It tastes kind of good.
It was.
All right. Our next example was the decomposition of iron 3 oxide. Now, this is one of those other examples that we included in our synthesis reaction when we talked about iron and oxygen. We also saw it in the combustion reaction, mostly because it's really easy to do and readily available. We also saw it in the law of conservation of mass. And in all of those, it released energy when we combine those two elements together. Now, we can also just decompose this iron 3 oxide, also known as rust, if we reapply all the energy. Basically, take that energy curve and reverse it. So it's harder to reverse because there's a much larger amount of energy needed. If the initial reaction to synthesize it was exothermic, obviously it lost a lot more than it gained, so we're going to have to replace that. But there are devices that can do that. For example, it's possible to get laser rust removal, which applies enough heat and energy to the iron 3 oxide to cause it to decompose back into the iron metal and release the oxygen gas in the air. So let's take a look at that example. Note that when we're playing it, you're going to see some little dusty particles floating around. The laser does evolve enough heat that it does sublimate some of the rust as well, meaning that it goes from a gas to from a solid to a gas. But for the most part, it is also decomposing the iron 3 oxide back into iron metal. Now, 2 other decomposition reactions that are pretty common. However, these don't really involve heat being emitted to it. It's not thermal decomposition, and it's not like a hard and fast rule like the way carbonates and chlorates would be. One other common one is the electrolysis of water, which is how we can get hydrogen gas and oxygen gas as well by itself. Now, this doesn't happen when you normally heat up water because water would just start to boil. However, if we run an electrical current through water, we can actually cause the water molecules to dissociate from each other. We can cause the hydrogen and oxygen covalent bonds to break, and then as a result, we're going to end up with hydrogen and oxygen gas. And what's interesting is because one of those the oxygens and the hydrogens have slightly different charges in the water molecule, those 2 gases form at different parts of the system depending on which way the electricity is being run through the water. And what we can do is we can actually collect those 2 gases into 2 different test tubes, and you'll see in this video as we electrolyze water and split it.
In the container is going to be some water that has baking soda mixed into it. The baking soda in the water allows electricity to flow between the 2 metal tips of the push pins. And so now you set them on the leads, and the electricity can flow between the 2 push pins now, and so electricity is flowing through the water, and so that's enough energy to break apart the water, make it undergo a chemical reaction so that the H2O gets broken apart into H2 and O2. It's going to be hydrogen gas and oxygen gas, and both gases are going to flow up through the test tubes, and one of the gases is going to be in one test tube and the other one's going to be the other one. How do you know which one's which? Well, if you take a look at the amount of gas in each test tube, there's going to be twice as much hydrogen gas as oxygen gas. So you can see in the right test tube, you have twice as much hydrogen gas as oxygen gas. This is how experimenters first learned that the ratio of hydrogen atoms to oxygen atoms in water is 2 to 1. It's 2 to 1 ratio, thus H2O.
Now, one other decomposition reaction is also the cause of the most highly requested demonstration every year, which sadly we are not in school to do. It is the decomposition of hydrogen peroxide. Now, hydrogen peroxide, H2O2, naturally decomposes into water and oxygen gas. It does it pretty slowly, but it does it over time. However, this reaction can be catalyzed. And remember, catalysts speed up reactions by reducing activation energy. They essentially make it easier to take apart the reactant molecules in some way, right? Less energy needs to be input into the system. Now, this decomposition reaction can be catalyzed by a couple different things: blood, yeast, potassium iodide. This is why, for example, some people put hydrogen peroxide on cuts to disinfect them because it kills bacteria, but you also see that it bubbles a lot when you do that. And it's because that blood that it's coming in contact with is catalyzing the decomposition. It makes it rapidly turn into oxygen and produce those bubbles. However, if we use a different catalyst instead of blood, let's use potassium iodide, but we can trap the bubbles with some soap, and that's what we call the elephant toothpaste reaction demonstration. Let's check it out. All right, so into the beaker, we're going to first put hydrogen peroxide. This is a solution of it. It's a lot more concentrated than what you would find like at home or in a drugstore. This is 30%. Typically you find like 6% at home. Now the bottle that this comes in actually, if you look closely, has these little pleats in it. And that's because the decomposition of this does happen naturally, and these allow the bottle to expand and grow. as it starts releasing oxygen gas, so that it doesn't build up and potentially explode. But like I said before, we can catalyze this reaction. We can speed it up using a number of things. Blood, for example, yeast. I'm using potassium iodide. I did dissolve this into a solution already, just so that it is already split apart into its ions. It'll help catalyze the reaction faster. But when we put this in, we should see the decomposition happen really, really rapidly. And like I said, it's just going to produce a bunch of gas, but if we add some soap to it, it'll help trap that gas, and we should get a bunch of bubbles and foam, as many of you have probably seen in the different demos and stuff online. All right, here we go. As you can see in the infrared camera, it's starting to glow a lot more now from the heaping released from this. Like I said, it's one of the decomposition reactions that's actually exothermic compared to most of them, which are endothermic. In the visible camera, you might actually be able to see some of the steam blowing off to the side as some of the water is evaporating from that released heat as well. Now, often you see this reaction done on demos using an Erlenmeyer flask, those triangular ones, or a graduated cylinder, where that long nozzle, similar to what we talked about in the combustion reactions, if we can control the way that the gas is released, we can give it a little bit more force. So those triangular flasks, the Erlenmeyers, help direct the gas in a more narrow area, increasing the speed at which it goes, which is sometimes why you see those big fountains on those demos in those videos. And one last decomposition reaction would be the decomposition reaction of sodium azide. Now, azide is not an anion that we've really talked about much, but sodium azide, it has the formula of NaN3. And when that is heated up, it's really unstable, and it ends up decomposing into sodium metal and nitrogen gas. This is actually the reaction that occurs inside airbags, or at least used to. They use a little bit more sophisticated compounds now. But in the initial airbags, what happens is when the car gets into an accident, a sensor sends a little electrical signal, causing some wires to get really hot, and that heats up the sodium azide and causes it to decompose and produce that nitrogen gas. And as a gas, it rapidly expands. Right, this reaction happens extremely quickly. It's a controlled explosion, essentially, causing those airbags to fill up and then protect you from hitting the windows or the steering wheel. Let's take a look.
Normally, something blowing up in your face is definitely bad. But right about now, this chemical reaction could very well save your life. It takes 50 milliseconds for you to hit the steering wheel in a crash. Everything we're about to tell you goes down even faster. Your car has to be able to detect when a potentially deadly crash is happening. You don't want your airbag deploying every time you hit a pothole or get in a fender bender. Your car has an accelerometer, several actually, in case one fails or goes off by mistake, that detects sudden, rapid changes in velocity. In one model, a ball bearing is normally held in place by a magnet, but in a crash, it comes flying free, and it flies right into an electrical circuit that tells the car's computer to deploy the airbags. Airbags don't just fill with gas like a balloon blowing up. That would be way too slow. The gas that fills airbags is actually produced by a chemical reaction. The classic example is sodium azide, which is stable until it's heated. In a crash, a small explosive or heating element called a squib goes off and ignites the sodium azide, which decomposes quickly to nitrogen gas and sodium metal. That sodium metal could react with water in the air to produce corrosive sodium hydroxide, so airbag manufacturers include some other compounds to react it into sodium oxide and alkaline silicate instead. By the way, the technology we described is a little old school. Nowadays, most frontal airbags are actually inflated with guanidine nitrate, but it works on the same principle as sodium azide. You're creating a lot of nitrogen gas. And accelerometers have changed with the times too. They're a little more sophisticated than the ball bearing thing. Meanwhile, the nitrogen gas is totally harmless, being the main ingredient in, air. Just a small handful of sodium azide can produce 67 liters of nitrogen. And that volume of gas creates enough pressure to fill the airbag in less than 40 milliseconds. So, quick first law refresher, an object in motion stays in motion. So when your car hits something, it stops, but your body keeps moving forward. And if it keeps moving forward right into the steering wheel or dashboard, that's bad news for you. So the airbag is there to slow you down more gradually than a steering wheel would. But this rapidly inflating cushion isn't actually pillowy soft. The front face of the airbag moves toward you at between 150 and 250 miles per hour. And if you were to hit it while it was still inflating, that might be almost as bad as hitting the steering wheel. To properly slow you down, an airbag has to have blown up already when you hit it. So that means the accelerometer detects the crash, the squib ignites the sodium azide, the nitrogen gas is produced, and in 50 milliseconds, it's already blown up in your face and started to wind down. Between 1987 and 2015, frontal airbags saved 44,869 lives. That's a summer evening at Dodger Stadium's worth of people, and a lot of people around to cheer thanks to one chemical reaction and some ingenious physics. Thanks for watching, and remember to drive safe. This explosion could save your life, but it's still better if it doesn't have to happen.